Welcome to the 17th Pfizer Colloquium of the Department of Statistics at the University of Connecticut. Since 1978, Pfizer Central Research has provided support for this program, and this support has allowed us to bring to our university the most distinguished scientists in the field of statistics. It has also allowed us to videotape these programs for the Archives of the American Statistical Association. The American Statistical Association and the University of Connecticut are both grateful to Pfizer Central Research for this continuing support. Now, to introduce our distinguished speaker for today's Pfizer lecture, I will call upon my colleague, Professor Rob Tibshirani of Stanford University.
So I'm happy to introduce Bradley Efron, this year's Pfizer lecturer. Brad was born in St. Paul, Minnesota on May 24, 1938, which might be called the first day of World War II. He got a Bachelor of Science in Mathematics at Caltech in 1960, and a Master's and PhD in Statistics ending in 1964 at Stanford. Since 1967, he's been a Professor of Statistics and Health Research and Policy at Stanford, and has had an endowed chair at Stanford since 1987. His professional contributions have been wide-ranging. At Stanford, he's been one of the prime builders of statistics, helping make it one of the best departments in the world over the past 20 or 30 years. He's been chair at Stanford, associate dean, and head of the faculty senate. He supervised many graduate students who have gone on to successful careers, starting with Norm Breslau in 1967, including Ron Thisted, Terry Thurno, and yours truly. Brad has won many honors, including the MacArthur Prize, membership in the National Academy of Sciences, the Reitz Lectureship, the Wall Lectureship, the Fisher Lectureship, and many honorary degrees. His research contributions have been deep, original, and far-reaching. To summarize these, I'm going to quote the great historian of our field, Steve Stigler, in an excerpt from the citation for Brad's honorary degree at the University of Chicago 5 years ago. Bradley Efron has revolutionized the theory and practice of statistical inference. He is widely recognized as the most original and innovative statistician of his generation. Early in his career, he made important contributions to geometric probability, design of sequential experiments, sensor data analysis, and the practical use of shrinkage estimators. Each of these has greatly influenced much subsequent work, but these were only a prelude to his great achievements in the years starting in the mid-70s. In a brilliant series of papers starting in 1975, he undertook a study of the structure of parametric inference using differential geometry in a deep investigation into the structure of exponential families of distributions. One consequence of this was his bold introduction in 1979 of a strikingly original and wonderfully general approach to analysis of complex data, the bootstrap. The bootstrap was the first of what have come to have been called computationally intensive statistical methods. It was a wonderful triumph of applied mathematics melded with numerical analysis. As he and others have subsequently developed it, the method has had a profound impact upon statistical practice, finding wide application in science and medicine. It is uncommon but not unusual for a single mathematician to advance his own subject significantly. Bradley Efron, by making major improvements on the quantitative methods that are used by all sciences, has done far more. His work has shaped much of our approach to modern statistics and will continue to advance our general knowledge in science and medicine for generations, to the great and lasting benefit of mankind. That's the end of the quotation from Steve. On a more personal note, I'll say Brad is not only a wonderful scientist, but a great friend to all of us who are lucky enough to know him. He's generous with his ideas and an inspiration to the field. I'm proud to introduce Bradley Efron.
Thank you very much, Rob. Rob's known for his humorous introductions at Stanford, so I'm pleased to have been spared that. Thanks to Pfizer Central Research and the American Statistical Association and Harry Poston, who has most of the hard work of organizing these really rather elaborate and valuable gatherings. And they've given me a stimulating double opportunity here today to speak both to those here and to future viewing audiences of the ASA film series. And the film series requires a general, not too specialized lecture. And my chosen title, The Statistical Century, is about as general as you can get and still use a noun. It doesn't even, it's ambiguous also. Which century was I referring to? Well, in fact, I was referring to two centuries. What has happened to statistics in the 20th century and what might happen in the 21st. Now, of course, there's a close connection between the two centuries. The past is a very uncertain guide to the future, but it's the only mirror we have, and we have to look through it. And so I'm going to begin in the past in just a few minutes. And the perceptive viewer or listener will notice that there's some peril here to the speaker. Predictions are particularly dangerous in a filmed lecture. because the film might be watched quite a bit of time in the future, in which case people get to grade you on accuracy. And I'll have to be happy with just a partial success, I'm afraid. I'll at least try and get the flavor of the history right. My first point, my main point in this lecture, and perhaps the most important one, is to remind you that statisticians are heir to a powerful intellectual tradition, one that's goes back a few centuries, but with far the greatest achievements and influence in since 1900. And viewed as a whole, the 20th century was really decisively successful for the rise of statistical thinking. We've become the interpretive methodology of choice in literally dozens of fields. Economics, psychology, education, medicine, lately in the hard sciences too, astronomy, geology, even physics, which used to disdain statistics, now has quite a bit of statistics in it. And if you go look at a physics journal, you'll be surprised to see statistics up there. Slide 1, the diagram, is supposed to represent a little automobile trip through the statistical century, through the 20th century, traveling between the three poles of statistical development: applications, mathematics, and computation. And I thought autos were the appropriate vehicle here because they were invented about 1900 also. And if I was really with it, modern computation, I would have done the lecture on a computer, and there'd be a little auto now that showed up and would drive around and would keep your interest, as they say. But I'll have to keep your interest myself, I guess. Our trip actually begins in 1899, just before the start of the 20th century. And I wanted to start there because there was already at that time an impressive list of statistical techniques available. Bayes' theorem, least squares, the central limit theorem, Galton's wonderful contributions of correlation and regression, binomial and Poisson methods. There had been famous statisticians already. But the list existed as a collection of ad hoc methods, not as a coherent theory. There was no real field called statistics, just some methodology clustered around particular application areas, like economics, public health, and government. And that's why I've started the trip near the applications pole. And if you go and look up a copy of the 1899 JASA, you'll see what I mean. The articles don't look like statistics articles. They look mainly like economics or government articles. And I doubt really that most scientists would have thought that there could be an independent field called statistics. Astronomers have stars, there's rocks for geologists, but what would be the subject matter of statistics? And information science was an idea that hadn't been formulated yet, but it was cooking, and it was cooking in the mind of a particularly important person, Carl Pearson. And the first step into the 20th century, 1900, is Carl Pearson's step, and it's a bold step. Pearson's chi-squared paper was a qualitative leap forward in applying powerful new mathematical techniques to statistics. Those techniques were matrix theory. And incidentally, statistics was ahead of physics in applying matrix theory. Pearson's paper greatly raised the level of mathematical sophistication in statistics. And I put 1900 there, but I also might have put 1901, because that was the year Pearson and Galton founded Biometrica, the first modern statistics journal. And there was a whole leap, suddenly there was a field called statistics. And I went and looked up the first issue of Biometrica. You can do that easily now on JSTOR. And it starts out with a charming essay by Galton trying to explain to biologists, I guess, what a CDF is. And Galton has a lovely explanation in terms of sticks put next to each other, characteristically clever and engaging. In 1908, we're moving along our path, our automobile trip. 1908 stands for Students' T paper, which seems simple in retrospect, was actually a very deep paper and had a particularly strong influence on the subsequent development, in particular on Fisher's ideas. It pointed toward a deeper understanding of statistical inference, one that applied in small samples, not just to census level samples. And that was a big difference. It implied that there was a much more precise theory lurking. And Student's paper greatly raised our level of statistical inferential sophistication. The most important date on my automobile trip for the 20th century is 1925. And that stands for Fisher's Great Estimation Paper. It's actually a second great estimation paper, but in this one he's got the theory really under control. And this single paper initiated a host of fundamental ideas. It's almost impossible to believe that you can have so much material in so much new and basic material in one paper. Consistency, sufficiency, efficiency, Fisher information, maximum likelihood estimation, and ancillarity all appear in this one paper. And most of the theory is fairly complete. It's pretty much the way we do it now. The biggest contribution of the paper, looked at from our point of view, was optimality, the best one can do in a given estimation problem. And optimality is the mark of maturity in a mathematical discipline or a scientific discipline in general. And for example, optimality theory is still missing and badly needed in computer science right now. They haven't had their Fisher. And I marked 1925 as the year statistics went from a collection of ad hoc techniques, ingenious but ad hoc, to a coherent discipline. And that paper has a lot to do with the reason we're all sitting here or standing here today. Well, I'm standing, you're all sitting. Fisher had some reservations about optimality, and I'll mention these in a minute. But once the mathematical optimality genie had escaped from the bottle, the automobile trip turned into a joyride toward the mathematics corner of the triangle. In 1932 represents Neyman and Pearson's fundamental paper on optimality theory for testing problems. And you'd think this would have pleased Fisher. Instead, it initiated a lifelong feud with Neyman. Some of this was personal jealousy or pique, but not all of it. Fisher felt that Neyman's approach could be optimal without being correct. And he had a favorite example, estimating the center of a random sample from a Cauchy distribution was one of his examples. And he said that the optimal, what we would call confidence interval, that is the shortest one for the distribution center, was optimal, but it wasn't correct, and that the correct interval should actually vary in length depending on how much information there was in the sample, Fisher information there was in the sample. And this is a subtle and I think important distinction. Correctness is one of Fisher's ideas that's definitely out of favor right now. But as I'll say later, it's hovering in the wings, and I think it's going to make a reappearance during the working lifetime of many of the people in this audience, many of the younger people anyway. I hope so, because it's an important concept. On with the trip. 1950 is an omnibus point there. You'll have to forgive my rather rough history. It stands for Wald's decision theory, and also for Savage and DiFinetti's subjective Bayes formulation, which actually came a little later. By 1960, when I jumped onto the statistics auto, my timing was poor, and it looked like our auto trip was going to end with a disastrous crash into the mathematics corner, which would be the end of statistics as an independent field. And it's no coincidence that 1960s mark the nadir of the statistics profession's influence upon statistical applications. Scientists actually can do statistics without a statistics profession. They can't do it very well, but they can do it, and they will if we don't give them the requisite help. Just in time, though, the influence of electronic computation began to be felt. Tukey in 1964 published a very influential article on the future of data analysis. And I've never gone back to the article to see whether his predictions were very accurate, but his spirit certainly caught the spirit of the times, or of the coming times. And the auto swerved suddenly toward the computation corner of the triangle. And fortunately, I think we didn't keep going in that direction either. If we had, we would have crashed into the computation corner and become a branch of computer science. That would have been the end of statistics too. But a further swerve took us back toward the center of the triangle, toward applications. And but now we were closer to applications again. But now with the statistics profession much better armed with computational and mathematical equipment. And it's a very happy development. We've become a lot more useful to our fellow scientists. The ones who use statistical reasoning are clients. And I've located 2001 at the center of the triangle, a healthy place to be. And the question marks indicate that I really don't know which direction or directions we're going next. I hope we're going in many directions, because that would be good. Some speculation will follow, or else there would be no 21st century in my talk. But there's one more feature of the triangle that will help me frame the question. I've labeled 1900 through 1950 the theory era. And that's when most of our current storehouse of fundamental ideas were developed. And this was the golden age of statistical theory, the time when the inside of our field was cultivated. 1960 through 2000, and I could say through 2001, is labeled as the methodology era. And during that era, this era, the theory from the golden age was harnessed with the power of modern computation to make statistics enormously useful to our scientific customers. And this has been another golden age for developing the outside of our field, the part of the field that faces our clients. On the next slide, slide 2, is a list of 12 important post-war developments that have had a big effect on applications. And the list isn't exhaustive. It's just my own favorites, plus the convenience of being able to list them in pairs. Somehow I find it quite natural to put these pairs in. And in making this list, I've pretty well restricted myself through 1950 through 1980, allowing 20 years for a little bit of perspective. Some of them actually came a little bit after 1980. So I'm going to go through this list and comment on it. The first pair is non-parametric and robust methods. Wilcoxon's little paper was actually only 3 pages long. Wilcoxon was a chemist who was interested in statistics and didn't like taking square roots. Wilcoxon's little paper set off an avalanche of new theory and methodology, as well as giving us the most widely used post-war statistical tool, Wilcoxon's test. Robust methods, a la Box, Tukey, Huber, etc., have had a slower growth curve, but they have made a marked impression on statistical consumers. And people ask me, people who don't know much about statistics, ask me, is this robust now every once in a while? Robust and non-parametric regression methods, smoothers, seem to be particularly current interest. The second pair, Kaplan-Meier and proportional hazards, progress in survival analysis has had a spectacular effect on the practice of biostatistics, and I can testify to that. I've been in half-time in the Stanford biostatistics program since my first appointment at Stanford, and I can tell you that the practice of biostatistics is much different now than it was in 1960, and I believe it's much better. In 1964, Steve Stigler had a nice paper, the same person who wrote so nicely about me, so I like his stuff. No, I like Steve anyway. Steve's had a good paper in the Statistical Science about the concerning which papers and journals have had the most influence in the post-war era. And it was a citation counting kind of paper. And Steve put Kaplan-Meyer's and Cox's paper, Proportional Hazards paper, as numbers 2 and 3 on the all-time hit, post-war hit list, sensational hit, following only Wilcoxon. The third pair is logistic regression and generalized linear models. And the extension of normal theory linear models to general exponential families has had its biggest effect on binomial response models, where logistic regression has totally replaced or almost totally replaced probit. And there isn't a big difference in actual computational details between logistic and probit, but there is a big difference in the depth of the theory that goes into the two, and carefully drawing the analogy with normal theory regression. And again, there's been a huge effect on biostatistics. Generalized linear models, GLMs, are now more popular for dealing with heteroscedastic situations than the Box-Cox transformation method, which in the 1960s looked like it was going to claim the field. I only mention that to show that tastes and methodology do change. And I think that was a good change, but it's not necessarily a good change. Overall, there's now a much more aggressive use of regression methods on non-normal data. The fourth pair on my list is the jackknife and the bootstrap. Kanui's original goal of non-parametric bias estimation was extended to standard errors by Tukey in what must be the most famous abstract of all time, because there's never been he never wrote the paper. The bootstrap did more than automate the calculation of standard errors and confidence intervals. In some sense, it automated their theory also. And the success of resampling methods has encouraged attempts to automate and extend other areas of traditional statistical interest, in particular Bayesian inference. And that brings us to the next pair, the EM algorithm and Markov chain Monte Carlo. This pair, these are computer-based techniques for finding maximum likelihood in Bayes estimators in complicated situations. MCMC, Markov chain Monte Carlo, including the Gibbs sampler, has led to a revival of interest in the practical applications of Bayesian inference. And personally speaking, I've been much more interested in Bayesian inference since it's gotten back on the practical track and out of the theological realm that it occupied for about 100 years. The sixth pair is somewhat different. Empirical Bayes and James Stein estimation. They're very closely related, and I believe this is the biggest theoretical hits since post-war on my list. It's different. This pair is a little different because it's not purely methodological. This is also a theoretical advance, as I'll talk about more soon. They're the biggest theoretical achievers and the biggest underachiever in volume of practical applications compared to the rest of this very robust list. And the irony here is that these methods, the two I'm talking about now, offer potentially the greatest gains over their predecessors. In fact, Wilcoxon's test is not a big improvement over the t-test, at least not in experienced hands. Experienced applied statisticians always knew how to use the t-test in a way that didn't get over-influenced by outliers. Empirical Bayes ideas can easily reduce risk or errors by 50% in favorable situations, and yet they aren't used very much. And I'm going to say more about this paradox soon. This list, my list of 12, is heavily weighted toward the outside development of statistics, ideas that make statistics more useful to other scientists. And it's crucial for a field like statistics that doesn't have a clearly defined subject area, such as rocks or stars, to have both inside and outside development. Too much inside development, and you wind up talking only to yourself. And the history of academic mathematics in the 20th century is a cautionary tale in this regard. There's been a lot of beautiful mathematics in the 20th century, but it's been aimed inside. It's beautiful to other mathematicians. And the mathematics as a departments in universities and in our whole society has definitely declined in importance from 1900 to 2000. So inside by itself is pretty dangerous, and I think we were getting close to that in 1950. However, outside by itself leaves the field hollow and dangerously vulnerable to hostile takeovers. And if we don't want to be taken over by neural networkers or machine learners or computer scientists, people who work exclusively in some interesting area of applications and have a natural advantage on their home turf, we have to keep thinking of good statistical ideas as well as making them friendly to users. You have to have a product as well as a sales force, and so far we've been doing pretty good with both things. Nobody was ever better at both the inside and outside of statistics than Fisher, nor better at linking them together. His theoretical structures connected seamlessly to important applications. And as a matter of fact, they caused those applications to increase in volume 100-fold in dozens of fields. And on this next slide, slide 3, I wanted to draw your attention to a few salient features of Fisherian statistics, Fisherian thinking, features that have been an important part of past statistical development, and by implication have to be strong candidates for future work. And a good part of this talk is aimed at future work and the people, especially the younger people in the audience, either here or on the film, who are going to be doing that work. And it starts out at the top of this by saying Bayes' frequentist compromise. When Fisher began his work in 1912, that's when he published his first paper, he was 22 at that time, Bayesian thinking of the kind of Laplace's kind, where you put a uniform prior on every possible parameter, that was advocated by Laplace in the 1780s and 90s. It was still prominent and perhaps even dominant in statistics. Fisher was dissatisfied with this kind of Bayes thinking, but he was not a pure frequentist, even though his work helped launch the frequentist bandwagon. And why wasn't he either a Bayesian or a frequentist? Why was he dissatisfied? I think this is more a question of psychology than philosophy. Bayesian statistics is a very optimistic theory that believes that the statistician only has to do well against the correct prior, which you can know if you work hard enough. Frequentists tend to be much more conservative, or at least more conservative. One definition of frequentism being trying to do well against every possible prior, or at least not do disastrously badly. Minimax being the ultimate expression of that philosophy. Fisher fell somewhat in the middle of the optimist-pessimist statistical spectrum, about the right place for most applications that I run into, which are neither very easy nor horribly, perversely hard. And to my reading, Fisher's work seems like a series of very shrewd compromises between Bayes and frequentist thought, but with several unique Fisherian features that nicely accommodate statistical philosophy to statistical practice. And I've listed some of the main points on this slide. The first one being direct interpretation of likelihoods. And this is the philosopher's stone of Fisherian statistics. If a complete theory of direct interpretation of likelihoods existed, we could shortcut Bayesian and frequentist methodology completely and go directly to an answer that combines the advantages of both. And Fisher had a big success along these lines, and it's called maximum likelihood estimation, which remains as the key connector between statistical theory and statistical applications. Could there possibly be a more useful idea? I've used it myself 1,000 times or 10,000 times, both in theory and in practice. Maybe not, but MLEs have a dark side that I'll get to in a few minutes. Fisher had a sensational failure to go with the MLE's success. Fiducial inference, generally considered, when it's considered at all, is just plain wrong these days. However, Fisher's failures are more interesting than most people's successes, and the goal of fiducial theory to give what might be called objective Bayesian conclusions without need for subjective priors continues to attract interest from people, including me. Reduction to simple cases. Fisher was amazingly resourceful at reducing complicated problems to simple ones, and therefore figuring out correct answers. And remember, correctness was big in his mind. And here are some of the methods he had. Reduction methods. Sufficiency, ancillarity, conditionality arguments, transformations, pivotal methods, geometric arguments, asymptotic optimality. Only one major reduction principle has been added to Fisher's list, and that's invariance, and even that's not in very good repute these days. And we could badly use some more reduction principles in dealing with problems like model selection or prediction or classification, where Fisher hasn't done all the hard work for us. The automatic algorithms and the plug-in principle are important because I think they explain Fisher's continuing popularity. Fisher seemed to think naturally in algorithmic terms. Maximum likelihood, analysis of variance, permutation tests, they're all based on computational algorithms that are very easy to apply in a routine way. That's not true of most frequentist methods like minimax or uniform minimum variance unbiased estimation, and it's not true of Bayesian statistics either, unless you're a Laplacian type of person. Plug-in is an awkward term, but I don't know a better one. It refers to an extremely convenient operational principle that Fisher did not invent, but he used all the time to great effect. To estimate the variability of maximum likelihood estimate, first derive and approximate formula for the variance from Fisher information considerations, and then plug in for any unknown parameters, plug in the maximum likelihood estimates of those parameters. So you use maximum likelihood to find out the accuracy of maximum likelihood. And when this principle, when it can be trusted, gives the statistician 7-league boots for striding through practical estimation problems. That's why MLE is so invaluable. If this description sounded a little bootstrap-like to you, it's no accident. The bootstrap is a good modern example of the plug-in principle in action. The bootstrap skips the hard work of deriving a formula by using a computer to directly plug in for the observed data for the calculation of a variance or a confidence interval. Exactly when the plug-in principle can be trusted is an important area of future basic research. The principle is deeply connected with unbiased estimation, or nearly unbiased estimation, and its theory gets dicey when there's too many parameters to plug in. I've gone on a little about Fisher because he's so crucial to 20th century statistics, but also because we seem to be reaching the limits of where his ideas and those of Student, Neyman, Pearson, Savage, DeFinetti, etc. can take us. Fisherian statistics has been criticized, justly I believe, for its over-reliance on normal theory methods. But during the last 20 years, we've sort of patched that up. Developments like generalized linear models and non-parametrics and robust regression have made us less subject to normality. We haven't been nearly as successful in freeing ourselves from another limitation, an excessive dependence on unbiasedness. It wouldn't be misleading to describe the 20th century as 100 years of unbiasedness. Following Fisher's lead, most of our current statistical practice revolves around unbiased or nearly unbiased estimates, particularly MLEs, and tests based on such estimates. And it's the power of this theory that has made statistics so important in so many fields these days. But we say in California it's power purchased at a price. That's a provincial joke because we exceeded our power capabilities this year, and we all are paying the price in our electric bills right now. The price of the classical approach to statistics is that the theory only works well in a restricted class of favorable situations. And good experimental design amounts to enforcing those situations, basically a small ratio of unknown parameters to observed data points. The ideal is to isolate the question of interest in a single parameter, the treatment effect, which is only achievable and at great expense and effort in a randomized, double-blind, controlled experiment. And this is a powerful idea, but a limited one, and we seem to be rapidly reaching the limits of 20th century statistical theory. Now it's the 21st century, and we're being asked to face data sets that never heard of good experimental design. Sample sizes have swollen alarmingly, the number of parameters more so. Even a moderate-sized medical database can hold millions of data points and raise hundreds of thousands of interesting questions. The response to this situation, which has come more from those who face such problems than from the professional statistics community, has been a burst of adventurous new prediction algorithms, neural networks, machine learning, support vector machines, all under the generic term data mining. And the new algorithms appear in the form of black boxes with enormous numbers of knobs to twiddle, that is, free parameters. And they have some real successes to their credit, but not a theory to explain those successes or to warn of possible failures. And the trouble is that the new algorithms apply to situations where biased estimation is essential. And we have so little biased estimation theory to fall back upon. Fisher's optimality theory, in particular the Fisher information bound, is of no help at all in dealing with heavily biased methodology. And in some sense, we're back at the beginning of the automobile trip, with lots of ingenious ad hoc algorithms, but no systematic framework for comparing them. I've been speaking in broad generalities, which goes with the turf of speaking about history and prediction, but for some relief both to myself and to the audience here and in the future, I wanted to discuss a specific big data problem of the type where classical theory is inadequate. And I've chosen a microarray problem mainly because I'm working on it right now with Rob Tibshirani and John Story at Stanford, but also because it's nicer than most such problems in giving at least a hint as how it might be approached theoretically. And that's what the next slide concerns. Microarrays measure expression levels, how active a particular gene is in the workings of a living cell. For example, is gene X more active or less active in a tumor cell compared to a normal cell? Expression levels have been measurable for some time, but it used to take on the order of a day to measure one of them for a talented experimentalist. Now, with microarrays, their charm is that they can measure thousands of gene expression levels at once. And this represents a 1,000-fold advance for biologists, the kind of lift statisticians got from the introduction of computers. But along with all this data comes from serious data analysis problems, and that's where we enter the picture. In the experiment I'm going to discuss, each microarray was reporting gene expression levels for 3,200 individual genes, the same 3,200. And the experiment in breast cancer tumor cells. And the experiment involved 15 microarrays, one for each of 15 tumors from 15 different women. And the first 7 tumors came from women known to have an unfavorable genetic mutation called BRCA1, BRCA1, while the last 8 came from women having another unfavorable mutation, BRCA2. The mutations, which are on different chromosomes, are both known to greatly increase the risk of breast cancer, up to about 80% lifetime. And a question of interest to Hedenfalk et al., the authors, is which genes express themselves differently in BRCA1 as opposed to BRCA2 tumors. So they're trying to get some idea of the mechanism. And this is a fairly modest-sized experiment by the current microarray standards, but it produced an impressive amount of data, 3,200 by 15 data matrix, each of the 15 columns being the 3,200 measured expression levels for that tumor, that microarray, and each row of the matrix being the 15 numbers, 7 BRCA1 and 8 BRCA2 for that gene. So you have to imagine a big matrix, 3,200 by 15. And if we had just the 15 expression numbers for a single gene, like gene 1 on the slide, the first row of the big matrix, we might very well run a Wilcoxon 2 sample test to see if BRCA1 was different than BRCA2. After all, that's the post-war favorite. We rank the 15 numbers, add up say the BRCA2 ranks to get the Wilcoxon rank sum statistic W, and then unusually big or unusually small values of W will indicate significant difference between BRCA1 and BRCA2 expression for that gene. For gene 1, as you can see, the 8 BRCA2 measurements were mostly larger than the 7 BRCA1 measurements, giving a big W, 83, and the two-sided p-value for the usual Wilcoxon test is 0.024. So if we were only considering gene 1, we would usually reject the null hypothesis of no difference and say, yes, indeed, BRCA1 tumors are less active than BRCA2s for gene 1. Gene 2 is significant in the other direction. Gene 3 isn't significant in either direction. And the trouble is, of course, we have 3,200 Wilcoxon tests. In the next slide, slide 5, the histogram in the next slide is a histogram of all 3,200 W scores. The histogram is obvious which one's there. And to make it easier to look at, I've drawn a smooth dashed curve through the histogram called f hat of W. And what you see right away is that f hat of W is a lot wider than f naught of W, the Wilcoxon distribution, the solid curve, that would apply if nothing at all was going on. That is, if all 3,200 genes satisfied the null hypothesis of no BRCA1, BRCA2 differences. And certainly this can't be the case. The two curves wouldn't be so different if it was. In fact, 614 of the 3,200 genes are significant at the usual 0.05 one at a time level. But of course, we'd expect 160 false significances if nothing was actually different, because 160 is 5% of 3,200. So how can the statistician decide which of the 3,200 genes are actually different between BRCA1 and BRCA2 and which is just noise? And the reason I bring this up is that the answer, at least one answer, involves looking at the problem from an empirical Bayes point of view, a la Robinson-Stein, our underachiever pair on the list of breakthroughs. And the very simplest Bayes model just assumes that there are just two classes of genes, those that are expressed the same for BRCA1 and BRCA2, and those that are expressed differently. And that for those that are the same, W has the usual Wilcoxon null hypothesis distribution, and that for those that are expressed differently, it has some bigger, wider distribution. And we don't know what that is, the wider distribution is, from theoretical principles, but we get a good idea from f hat of W, the empirical distribution through the histogram. And it turns out that it's very easy to write down Bayes' rule for the a posteriori probability that a gene is actually different given its W score. And that's on the next slide, slide 6. And it turns out that the rule, I've written down the rule for you, though you don't have to look at it because I'll just show you the data. The rule only depends on the ratio of the two curves, the ratio of f naught, the Wilcoxon distribution, to f hat, the empirical distribution. And the graph on the bottom of the next slide, the heavy curve is the a posteriori probability of a gene being, quotes, different as a function of its Wilcoxon score, W, in this particular example. And it turned out that in order to have a posterior probability of different, greater than, say, 90%, quite different, that is, a gene's W score needed to be among the 3 smallest or 3 largest possible W values. That compares with among the 12 largest or 12 smallest for the 0.05 significance. Only 67 of the 3,200 genes showed such strong results. And the criterion is certainly a lot more stringent than the one that gave 614, the one at a time 0.05 test. But it has a good Bayesian justification, and it also has good frequentist justification in what's called terms of false discovery rate, which I won't be able to go into here. Nice new simultaneous inference testing technique by Benjamini and Hochberg. The main point of the example, and the reason I brought it up in the middle of a philosophical discussion, is that it's definitely post-Fisherian in nature. It's empirical Bayes in the sense that it begins with a pure Bayes setup, but then estimates a crucial part of the resulting Bayes rule from the data. And I said that we have a very little theory to fall back upon when we want to use biased estimation. The great exception is Bayesian theory, which provides a very satisfying framework for optimal decision making when we have reliable prior. And of course, the absence of a prior in practical problems is what drove Fisher and the rest of us away from Bayes, most of the rest of us away from Bayes in the 20th century. Robbins and Stein's crucial insight was for that problems with parallel structure, like the microarray situation, we can use the data itself to generate the prior. And from this point of view, having all those genes, 3,200 of them, starts to look more helpful than distressing. And for the purposes of learning about the prior, 3,200 is preferable to having just 10 or 20. So another way to say this is that multiple testing problems get easier rather than harder when you have a lot of things to test. Most talks about the future are really about the past or the present. This one's no exception, but I will make one firm prediction that research on the combination of Bayesian and frequentist philosophies and methodology will be a crucial part of 21st century statistics. Am I most hopeful? I can imagine a new theory of statistical optimality, one that says what's the best one can do on, say, the microarray problem. Maybe I'm being too hopeful here. Most large data sets aren't like this and don't have all this parallel. The microarray example is big data because a lot of small experiments have been repeated in a parallel fashion, and most data sets aren't of that form. But statisticians are more than just passive processors of whatever data happens to come our way, and if we can show scientists that we're good at doing parallel processing analysis, then we'll start getting a lot more parallel processing data sets. At least I hope so. That's the end of the example. Back to generalities. Someone once told me, and I heard this again today at lunch, that the intersection of all the countries that have been called Poland is Warsaw. And I mentioned this because if there were a geographical analog to the statistics profession, it might be Poland. Strategically located, surrounded by powerful and sometimes aggressive neighbors, and still maintaining a unique and vital national heritage, able to produce a Jersey Neyman, for example. Statistics had a much better 20th century than Poland, but Poland is still prominent on the map of Europe and doing pretty well these days. Statistics is doing pretty well these days too. We tend to think of statistics as a small profession, perhaps comparing ourselves with biology or computer science, but in fact we aren't so small. We're bigger than astronomy and a little smaller in numbers than geology, and we're particularly not so small when you consider our importance to the scientific enterprise. How will the statistics profession do in the 21st century? That's up to you, particularly the younger members of the audience, both here and film-wise, who form the next wave of statistical researchers. Fields like ours prosper in proportion to their intellectual vitality, and I hope you'll be able to add a whole bunch more to my list of 12 important methodologies by, say, 2025. One last slide. One can make a good case that we are the ones living in the golden age of statistics, the time when computation has become faster and cheaper by factors of 1,000,000, and when massive data collection has become the rule rather than the exception in most areas of science. Statistics faces many great intellectual challenges, not to mention the usual financial and academic ones, but our record in the 20th century gives me at least a lot of confidence in facing the 21st. And I thought I'd finish as I began with a statistical triangle. We had barycentric coordinates when I was a student, and I learned it really well. In this time, the triangle corners are the three three competing philosophies of statistics: Bayesian, frequentist, and in the middle, Fisherian. And I've tried to allocate the influence of the three philosophies on some important current areas in statistics. Some of the topics are easy to place, like partial likelihood and conditional inference belong up near the Fisherian pole because David Cox is our leading Fisherian. Robustness and non-parametrics follow Huber and Tukey's preference for being frequentists. The Bayesian pole certainly gets credit for multiple imputation in the Gibbs sampler. I placed the bootstrap somewhere halfway between Bayesian, frequentist, and Fisherian, and I put empirical Bayes halfway between Bayesian and frequentist. Other topics aren't so clear-cut, as you can see by my somewhat weaselly placement of the EM algorithm right in the middle of the triangle. The EM is tough because actually Fisher was the first EM person, but then the theory got a lot of input from both Bayesians and frequentists, so I don't know where to put it, but obviously all three have contributed. The reason for the diagram and the important conclusion for future work is that all three of the competing statistical philosophies are alive and contributing well to active research. And personally, I'm quite happy to use whatever philosophy seems most effective for any given problem, but it's at least valuable to know what intellectual tools are available to us and what their past successes have been. Some recent developments in algorithmic prediction models don't seem to fit into the triangle very well. The prediction culture, as Leo Breiman calls it, which includes neural networks and data mining and support vector machines, has grown up in the front lines of the struggle with massive data sets. And I think it's reasonable to expect brave new statistical enterprises to begin with a burst of pure data analysis. And the innovators may even be openly scornful of the old statistical guard. This is the teenage rebellion phase of new methodology, and the rhetoric at least shouldn't be taken too seriously. The great achievement of 20th century statistics was putting a firm foundation under the older ad hoc methods like regression and design. That is, to locate them within the statistical triangle. And this was a great aid to both the development of better methodologies and also the development of a more powerful statistical theory. Things went back and forth very nicely between those two. The new generation of statistical researchers faces the same challenge with the prediction culture. At some point, the questions of optimality and inferential correctness have to be faced even by elaborate prediction algorithms. Based on our past record, we can reasonably expect success. Maybe we can even hope for an expansion of the theoretical basis of statistical inference so that the Pfizer lecture of 2025 will have to have a square instead of a triangle there. I hope so. Finally, let me thank both the ASA and Pfizer Central Research and the STORS Department too for this opportunity to talk about my very favorite subject, statistics. We can all be proud of belonging to a profession that has done so much to foster clear thinking in science, government, and industry. Thank you very much.
Thank you, Brad, for a very fine and stimulating perspective on the development and history of and the future, I should say, of our own field. Thank you very much.